In this lesson, we are going to do several word problems involving exponential growth and decay. And for that, we're going to have to introduce the formula of y equals art, as if it looks like. Y equals a times r to the t. An example of these are both listed right here. You can see this is not in your notes, so you can just take a look at this. But it says, the first one on the left is exponential decay. So it's when the value of a is greater than 0, but the b is between 0 and 1. So that's the r part, actually. And then you'll notice in the second example, it's when our rate, is greater than 1. And so we'll have to figure out how we're going to come up with that when we do our word problems, but each situation will be a little bit different with that, and you'll kind of catch on to the pattern. Here's some questions students will have after we start studying exponents for a little while, is why can't r be 1? For example, here we have y equals 3 to the 1, 3 times 1 to the x. If r is 1, you'll notice when the table I made to the right, when I plug a 1 in for every single time, no matter what I do, I get a 3. And so it's either going to be between 0 and 1 or greater than 1. Your base can't be a 1 because that wouldn't give you any difference. It's just a horizontal line. And then we've done this one before, but just to point out again why our r can't be negative. Sometimes when we have a decrease, students want to plug in a negative, like if something goes down 30%, they want to plug in negative 0.3. But this, if you look at this table, you'll notice that every time, and this is what we talked about before, is every sign would change. So we go from negative 6 to 12 to negative 24 to 48. It doesn't graph exponential growth or decay. It's just kind of a scatter plot, it looks like, so no pattern there that we would recognize. So for what we're doing today, you'll see at the top of your notes, we have the formula for exponential growth and decay. Looks the exact same. The only difference is that in the growth, the r is greater than 1, and in decay, r is between 0 and 1. Again, remembering it can't equal 1 because that'd be a horizontal line. So what our variables stand for is y is the amount at time t, a is the initial amount, r is the rate of increase, and t is time. You might be thinking for exponential decay, rate of increase doesn't make sense, but what's going to happen is our rate of increase is going to be between 0 and 1. So it'll be something like 50% or 80%. So it's the decimal 0.5 or 0.8, where really it will be a decrease because it's lower than 100, and so you'll see that in the graph once we get to those problems, I think. So to kind of just jump in and start working with these. Our first one says, in 1985 there were 285 cell phone subscribers in the town of Centerville. The number of subscribers increased by 75% per year after 1985. How many cell phone subscribers were in Centerville in 1994? So would this be considered exponential growth? Think of cell phones. When we talk about exponential growth, remembering exponentials means that we are taking something to a power. So when we square something constantly or cube it, that number goes up really fast, doesn't it? Think of just the number 2. We go 2 squared is 4, and then we have 8, 16, 32, 64. It's doubling all the time. And so when we have exponential growth or decay, it's either going up very quickly or down very quickly. In this problem, we have to first decide if we have growth or decay. So if the number of cell phone subscribers increased by 75% per year, that would be considered growth. So we're using our value of r is greater than 1. Now we're given the 285. You'll notice I kind of color-coded here. 285 is the purple, just like our A. That's our initial amount. That's how many people were using cell phones in 1985. And so we're going to start out using our formula that's given, but we're looking for the amount at time t. So we're looking for how many people in 1994. So we'll say y equals, and our initial amount is 285, times r. Now remember, our r has to be greater than 1. Because they tell us the number of subscribers increased by 75%, what they're saying is 100% of the people who were using them in 1985 are still using them, plus another 75%. That's what that's saying. So it's not 0.75 that we use. 100% of the people that were doing it are still doing it, an additional 75%. So we're really at 175%. Which sometimes we think we can't have that, right? But with growth, that's how people talk. You'll see things on the news sometimes, they'll say that company grew by 300%, which in our minds sometimes we think things can't be over 100%. But there's an example of everyone stayed the same, plus they had more people join in. So that's hopefully makes sense to you. If I'm going to write that as my rate, I would put that instead of a percent, I'm going to write that as a decimal. So my r is 1.75, which is how I have one that's greater than 1. So you can see how that's growth then. And then it's raised to the t. T is our time. So I'm looking for 1994. How much time has passed from 1985 to 1994? That would be 9 years, right? I'd subtract 1994 minus 1985. So my T value is a 9. So in my calculator right now, and I can show you how we would do this, I'm going to go ahead and you guys can do the same thing. I'm going to punch in 1.75 to the 9th power. So 1.75 raised to the 9th. And then you would take that answer times 285. So there, remember the question asked how many cell phone subscribers were there in 1994? We would say 43,871 people, or if we wanted to round up. And here the rounding isn't really a big deal. We're able to get away with rounding up or down even though it's people. We're going to say our Y value then is 43,872. I'm not going to write a decimal because I know I'm talking about people. So this is what we think, and actually, let's be a little more accurate. Since I did round, I'm going to say approximately. So in 1994, there were approximately 43,000 people who were cell phone subscribers versus 285 in 1985. An example of exponential growth that you'll see a lot in everyday life is cell phones, and that's kind of gone down a little bit now because we've already hit that peak where almost everyone is having a cell phone. Now you're going to see that it's going to be things like iPads or Kindles or those kind of, they're saying that desktop computers are no longer going to be something we see anymore. People are not going to buy desktop computers, and you even in your own home might not have that. I'm wondering when teachers now, we've had desktop computers forever, I'm wondering when they're going to start giving us laptops to just bring back and forth from work and home. But they're just not, they're kind of obsolete. There's exponential growth going on with the Kindles and the iPhones and iPads and all of those things, and who knows what's coming next. But they've kind of hit their peak, and desktops, they're kind of obsolete now. Are kind of going out like the DVD players would with the Blu-ray or the good old VHS tapes that I had when I was growing up. So that's this kind of stuff. Technology-wise is a huge area for exponential growth, and I think we'll just continue to see that as we get older. But there's our answer for number 1. So now we'll try another one. Hopefully that formula made sense to you. In this one it says the population of a city of 1 million is increasing at a rate of 3% per year. If the population continues to grow at this rate, in how many years will the population have doubled? The reason that this would be an important question to ask is cities need to plan ahead for their growth. If they're growing at a certain rate or they're declining in their growth, they need to know that for things like schools. Some of the suburbs like Waconia, I'm thinking as an example, they all of a sudden were a city that just blew up, and they did not have enough schools to support the people. And people aren't going to move to your city if you don't have schools. And so when they have huge growth and they're growing at a really high rate, they need to plan ahead and say, okay, we're going to need a new elementary to have all these kids that are showing up in our district come in, or a new high school or a new middle school, whatever it would be. We need to have another library. We need more sports facilities. We need some more parks. All of those things that cities need to plan for if they're continuing to grow. And they will plan for that based on math. I mean, they're going to look at the data and decide, this is really a statistics problem. They're going to decide if they should be growing these things because they'll have more tax money coming in, so they'll be able to pay for this. And they don't want their city to stop growing, because then the more people that are there, the more revenue the city brings in and the more they can do. And so this city's looking at how many years will the population have doubled. So since the population's doubling, hopefully you recognize this as a growth problem. Our R is greater than 1. What we're given is that 1 million would be, that's the A value, right? That's its initial amount. And what else are we given? The rate is 3%. So we're going to say it was 100% of the people that are there, plus another 3%. So we're at 103%, which makes my decimal 1.03. What we don't know is, it says how many years will it take for the population to have doubled. They're looking for us to leave T as a variable. So I have my A of 1 million, my R of 1.03, and my T is my variable. Now my Y value, remember Y is the amount at time T. So when we find T, they want to know how many people it is. Well, it says when will the population have doubled. So since we know it was 1 million, doubling would make it 2 million. They don't tell us that number, they expect us to dig that out of the information. So this is my equation. I want to know how long will it take for the population to go from 1 million to 2 million people in this city. To solve this now, hopefully you recognize this is why we learned about logs. I have a variable in the exponent. So the first thing I would do to solve this is I'm going to want to get my 1.03 to the t by itself. So I'm going to divide by 1 million. And I would then have 2 equals 1.03 to the t. Now I'm thinking I can't make 2 and 1.03 be the same base. So what I'm going to do is I'm going to take a log to both sides. So log of 2 equals log of 1.03 to the t. And then, because I'm in log form here, I can use my power rule, and I can put that t out in front. Now, to get t by itself, I just have to divide by the log of 1.03, and I'm going to have my t. And I'm going to put approximately because I know I'm going to have to round. So on my calculator, I'm going to say log 2, or just 2, how about log 2, and then divided by log of 1.03. And I get 23.4498. So when I go back here, and I'm going to write my answer of 23, remember in logs we round 4 places. So to answer the question, how long will it take this city to double its population? We would say in about 23 years, the population will double. I don't think the city wants us to find the exact hour it's going to double. They know this is an estimate. So if we were to take 23.44 to find 0.4 of a year would be about 5 months or whatever it would be. So we're not going to say in 23 years, 5 months, 7 days, 3 hours. We don't need to be that specific. If we say in about 23 years, your population is going to double. The city then could plan some projects and put some money away for making sure that they are growing at that rate. And even during that time, they're still going to double check at times that their rate is still 3%, because that could change, couldn't it? I mean, a city could all of a sudden not be growing if they lose a major business in town, or they don't have the same employers they did before. They're not going to continue that rate of growth, so they would check that during that 23 years also. But hopefully that made sense for where we got that answer, so we got to use our logs. We'll try the next one now. This one can be a little bit confusing because we're comparing two things, so make sure you pay attention to how we set it up in the reading of the problem. In the year 2000, Nigeria had an estimated population of 127 million, and the United States had an estimated population of 278 million. So this is from our 2000 census data. Nigeria's population is projected to increase 2.6% each year, while the United States population is projected to increase 0.9% each year. When will Nigeria's population be more than the population of the United States? Use either model. So we're going to do growth or decay. I think for this we're saying that the population is growing, right? So we realize that's a growth problem. And what we're going to look for is we're going to say we're trying to find when Nigeria, their population, is greater than the United States. So when I set this up, I'm going to say their AR to the T is bigger than our AR to the T. So what we know for each of them is Nigeria had an initial population of 127 million. So I'm going to say that's their A, 127, and I'm going to leave this and just realize that I'm talking in millions. I'm going to write 127, and then I'll answer in millions when I'm done. And as long as they're all in millions, I'm fine. And since they're growing at 2.6%, that'd be 102.6 growth. So I'm going to use 1.026, and we don't know how long it'll be until they're greater than the United States, which is right in 2000 was at 278 million, and we were growing at 0.9%, so as a decimal that'd be 1.009 to the T. Hopefully you see where I got that. I'm saying that our growth, when is Nigeria's growth greater than the United States? So now I'm going to solve this for t. So we're going to see really what happens here. Even though I have the greater than sign, I'm actually going to find when they're equal. So we'll find the exact point where our populations are equal. And since Nigeria we know is growing faster, anytime after that point is going to be when Nigeria passes us and is higher population than us. So to do this first, I'm going to have to think about how I use my logs here. If I want to add a log to both sides, I right now have the log of 127 times 1.026 to the t. In logs and exponentials, we have multiplication really means addition, right? So I can separate this out, and I could write this as the log of 127 plus the log of 1.026 to the t. Look at that for a second. If we were given the red, we would write it as the blue, wouldn't we? Because it has a plus sign. So I'm going to continue over here and say the log of 278 plus the log of 1.009 to the t. So now, as I want to try to solve this somehow, I know that I'm probably going to use my power rule again, right? And put this t out in front right here. And I'm going to put this t out in front right here. Now with all of these logs, it can get really confusing. So I'm going to actually find the decimal value for every single log. So I'm going to punch in the log of 127, and I'll get 2.1038 plus, and then I'd have the log of 1.026, which is 0.0111, and then I'll have that t behind it. I'm putting it behind now because I have a decimal there. And then is greater than the log of 278. When I punched that in my calculator, I got 2.4440 plus, and I punched in the log of 1.009, and I got 0.0039. Then I'll put that t behind that. So notice how I have variables and numbers. It's just like this equation. If I have 3 plus 2x is greater than 5x plus 7. We can solve that pretty easy by getting the x's together and the numbers together. Same idea here. I'm going to move my t's to one side. So I'm going to minus 0.0039t from the 0.0111t. And I would have 2.1038 plus 0.0073t is greater than 2.4440. So now I'll minus the 2.1038. So I have 0.0073t is greater than 0.3402. It's an easy algebra problem, but it can be kind of confusing because of all these crazy long decimals. So now to get t by itself, I divide by 0.0073. And I end up with t is greater than, and it's going to say 46.8897. So this is actually telling me the equal to, at that exact moment, at 46 years from now, or from 2000, excuse me, that's the moment, if we were to think of a moment, that's when Nigeria passes the U.S. in population. So we're going to say they want to know when will Nigeria's population be more than the population of the United States. So since in 2000 is when our data was given to us, and we know sometime in that year, 46 years later, and it's a decimal, right? So it's sometime during that year. So our answer would be in the year 2046, Nigeria's population should, and we're saying should because we know we're estimating and things could change, be greater than the United States population. So we still aren't there yet, right? This is data, and we would have to, they would look at this model and make sure that they're still growing at the same rates. There are things that could change this outcome, right? Let's say the United States typically has in the past had baby booms when we've had lower economic issues going on, and we are kind of in a, people would argue about our recent depression, and so maybe the United States is going to have a higher rate of growth because we're having another baby boom that we don't pick up on yet. Or maybe Nigeria is going to have something happen where they have an outbreak of some disease, and we know that they don't have the same medical things as we do, and so maybe their population is going to end up not growing as quickly because of something terrible that happens, or that has already happened since the year 2000. And so all of that could change, and this is actually, if you're looking at this problem, this really is a statistics problem. This is what you learn to do when you're taking AP statistics, is this kind of stuff. And you look at, is this rate still happening, when is that going to change, and what implications, what other factors are going to contribute to that population growing or not growing in those 46 years. So if everything stayed the same, in the year 2046, Nigeria's population would pass the United States. Doesn't mean that's going to for sure happen, but that's a prediction you could make. And you would, again, check data every several years just to make sure that that's going to keep up. So we're going to keep going. Those are our growth problems. Here we're going to look at some decay ones. So in number 4, it says HTI bought a computer for $2,500. It is expected to depreciate at a rate of 20% per year. What will the value of the computer be in 2 years? This is true of lots of things that we buy. We buy computers, they depreciate, right? Where there's no way I can sell a computer a year later for the same price I bought it for or more. When I buy a car, the second I drive it off the lot, it's not worth as much as when I bought it to begin with. And so we are used to things depreciating, and that's a common thing that you will see in your everyday life as an adult. You hope, like for example, right now people's houses are depreciating, or they have been, and we hope that they would appreciate because then we make money when we sell our house. That's one of those things, like maybe even your family hasn't been able to sell their house because they can't make as much as they paid for it. And that's something that people are dealing with now. And they're hoping that homes start to appreciate so you can make money on a house, because that's a pretty big investment for a family. So then this is an example of exponential decay. I'm still going to use the same formula. I have y equals a times r to the t. And we said they bought the computer for $2,500. So that's my a value. That's their initial investment. That's how much they paid at the start. And my rate, this 20%, if it's going down 20% a year, you would take 100% minus that 20%. Because that's how much it's actually worth. It's worth 80% of what you paid for it. So that becomes my r. It's 0.8. And that's how you'll always do those depreciation problems. You will subtract them from 100, because remember, r doesn't equal how much it's going down. R is its rate of increase. So it's how much it's worth. It's 80% of its worth there. It's not worth 20%. That's how much it went down. So it's worth the 80% of its total value. And then the time, it says, what will the value of the computer be in 2 years? So I'm going to put a 2 in here for time. And again, here now we're going to be looking for y. So we're looking for that amount after 2 years. I can punch this into my calculator. 0.8 squared, and then times the 2,500, and you should get $1,600 when you do that. So in theory, HTI could sell that really expensive computer for $1,600 2 years later. Next, it says a cup of coffee contains 130 milligrams of caffeine. If caffeine is eliminated from the body at a rate of 11% per hour, how long will it take for 90% of this caffeine to be eliminated from a person's body? So this actually is really interesting. This is how caffeine is eliminated from the body. If you think about it, when people have caffeine headaches, or they say you can get addicted to caffeine, you'll notice when we do this problem how long it takes to leave your body. So if you're having coffee every day, you still have a bit of caffeine from the day before in your body. And so that's how you kind of become dependent on it. So if you go cold turkey and have no caffeine, your body kind of goes through withdrawal symptoms. But we'll set it up and then we'll talk about it once you see our answer here too. Hopefully you recognize this would be an example of a decay problem. My 130 milligrams of caffeine is my A value. And it says that it is eliminated from the body at a rate of 11%. So remember that 11% is leaving our body, so we take 100% minus 11%. So what's left in my body is 89%. So we'll use 0.89 as our R. And then it says, how long will it take for 90% of this caffeine to be eliminated from the body? So we don't know the time. We're looking for T. What's confusing here is what we're going to use for our Y value. Remember, your Y is your amount. So if we have 130 milligrams to start, that's 100%, right? If I want to find 90% of that, I'm going to say 90% is eliminated from my body, so I'm taking away 90%. So I would take 130 times 0.9, and I would get 117. So this is how much is being eliminated. They want 90% of this caffeine to be gone from your body, which means how much is left over? 10%. So you still have 10% left in your body. So if you look at my numbers here, if I had 100% at 130 and we take away the 90%, we would still have 13 milligrams of caffeine left in our system. So that's the number that goes in for my y. Now if that's confusing to you, I want to just run through that one more time. We started with 130 milligrams, and they want to know how long it'll take for 90% to be gone. So I'm taking 90% away. So 90% of 130 is 117. If I take that away from 130, I have 13 left over. If you were thinking, you also could say, well, that means I just have 10% left. And you could have just taken the 130 times 10% right away and still gotten 13. Either way, that would work. So now that I see that this is my equation, I realize that I have a variable in my exponent, so I'm going to have to solve for t. My first step would be to divide by 130. So I would get 1/10. You might put 0.1 there, whatever you like. And then I have equals 0.89 to the t. I'm going to have to solve using log, so I'll take a log to both sides. And then I'm going to again use that power rule here and put that t out in front. So what we have here, that kind of looks confusing, is we have the log of 1/10 equals t times the log of 0.89. So to get t by itself, we divide by the log of 0.89. And when I punch that in my calculator, the log of 1/10 divided by the log of 0.89, I would get 19.7589 as my t value. So after about, we'll just round to the nearest hour, 20 hours, 90% of the caffeine will be eliminated. Now think of that as what caffeine does in your body. If I have just a coffee every morning with that much caffeine in it, after 20 hours, so almost till the next morning, I still have 10% left in me. I could plug in 100%, make that be a 0 and see when it lines up, or a even smaller amount like 1%. Excuse me. And we would see how long it would take for that caffeine to leave my body. Now, if you think of pop, when you have a pop or an energy drink in the morning and then you have one after school again, the caffeine from that drink you had in the morning is still in your system. And then you add the one after school, well, that compounds it and you have more caffeine in your system. And then if you go the next, even later in the evening and have another one and you wait till the next morning, over time all of this caffeine is building up in your system, which is why you can, they say, become addicted to caffeine. You have it in your system all the time, and if you go a few days without it, you go through that withdrawal and you can get that headache where you have, they say it's a caffeine withdrawal headache. And so that's kind of a big deal to think of that staying in your system that long, and maybe watching how much your caffeine intake is. I'll stop lecturing you on caffeine intake now, though. And we'll do our last problem. This one I think is interesting because this is something you guys will probably, hopefully do, right? Right out of college, you buy a condo for $85,000. You plan to buy a house in 5 years. If the condo appreciates at about 5% per year, what will it be worth when you sell it to buy a home? What if the condo depreciates about 3% per year? What will it be worth? So this is kind of a big deal. When you are looking to get out of college and you have student loans you're paying off and you want to live on your own, but maybe you don't want to live in an apartment. You want to try and buy a smaller condo so you hopefully make some money off it. You can deduct interest on that, and you won't have to just put your money into an apartment and waste what you think wasting money every month where you could be investing it. It's a big deal whether or not your condo appreciates or depreciates. So we're going to figure out both. So for appreciation, we'll just do two different ones. I'd have y equals ART again. And remember, we bought our condo for $85,000, so that's going to be my A for both of them. And if it's appreciating at 5%, that'd be 1.05, and we're looking for after 5 years. For the depreciation, I'm going to keep everything the same except my rate. So I'm still buying the condo, I'm sorry, oh yeah, there we go, for $85,000. And then we said it depreciated 3% per year. So if I take 3% away from 100, I'd have 0.97, and then to the fifth. So I would just punch both of these into my calculator. And for my appreciation, I get approximately $108,483.93. And then for my depreciation, I get $72,992. Oops, not $9.99. $992.39. That's how much my condo be worth. So here it's about $73,000, Here it's about 108,000. Here's the difference between homes that are appreciating and depreciating. And I want you to think about this when you think of your parents buying and selling a house. Appreciating, if I go just 5% per year, I'm making $23,000 in this house. So that's a nice investment for 5 years, isn't it? If I could put money into a bank and have it come out with $23,000 extra after 5 years, that's a good idea, isn't it? I could pay off a couple years of college, student loans, or buy a bigger house with this extra $23,000. That was a great investment. Over here, if I have depreciation, I am losing $12,000 in this condo. So when I go to sell it 5 years later, I actually am losing $12,000. Now hopefully I've paid off $12,000, depending on how much I've paid and if I had, what kind of loan I took out. But I might even be what's called underwater. You're underwater in your home here, where you owe more than what your home is worth. So let's say I'd only paid off a few $1,000s on that, because if you don't know what mortgages is, what happens is your first, like if you take out a 30-year mortgage, your first 10, 15 years, you pay almost only interest. There is very little that goes down on your principal for your mortgage. It's almost all interest. And so if you can make a couple extra payments a year, those first 10 years of owning a home, you really save yourself a ton of money in the long run. In this example, I'm not sure I'd pay off $12,000 in 5 years. In fact, I really doubt you would. So you would actually owe money when you try to sell this condo, and that would mean that you could buy less of a house when you're trying to buy a house. What you'd end up doing in the depreciation scenario is probably saying, oh, I better stay in this condo longer and hopefully not lose so much money because it's really hurting me. So that, when you hear about people talk about the housing market on TV, it probably doesn't seem like it makes much sense to you or matters much, but this is a big deal whether or not you are making money or losing money on a house. We have a difference here between those two options of $35,000. And that's some yearly paycheck. I mean, that's a whole year's salary right there for a lot of people. So that's kind of what appreciation and depreciation do in your everyday life. That's how you would use math. I know not many of you think you'll ever use the stuff we learn in our class, and for part of it you're probably right. You won't always use it. But the thinking skills behind it and the stuff like this right here, everyone's going to probably want to own a home. All of you that are listening to this video right now, your goal is probably not to live in an apartment your whole life. Not saying there's anything wrong with that. That just probably isn't your goal. You would like to own your own home. It's fun to be able to decorate your house and feel like you have some ownership in that. And that's probably a goal of many of you. And if it is, this is kind of a big deal for that. So I will get off my soapbox again and let you guys do your homework. If you have any questions on any of these, make sure you let me know tomorrow.